Hello? Can you hear me? Yep. Can you guys hear me in the back? So, good morning. I am Karl Schulz. I'm from TACC, the Texas Advanced Computing Center from UT Austin. And thanks to Sun for inviting me out to give a short talk today. So I was going to talk about the Ranger system, and Andy introduced it. I was going to go into a little bit more detail on the system and also kind of, give the proverbial experiences talk, if you will, kind of tell you, thanks a lot, some of the things which went good and some of the challenges that we faced. So in terms of an outline for this morning, I'll go over the sort of the team that's involved in putting together Ranger, some of the costs associated with the system, go ahead and show some obligatory deployment pictures because you kind of have to do that, and then talk a little bit about our HPC software stack that we have implemented on the system today, and then go through some experiences, some of the challenges, like I said, that we faced, and give you some example, just a couple of quick application examples, and also some raw performance data from the system and some early usage. So just to give a little bit more background behind Ranger, if you're not familiar with how this came about, this really is a very unique instrument for computational research. It is housed at our new machine room, so TACC is fortunate to have a new machine room as part of this deployment. On the right, you do see the completed system. It's an enclosed hot aisle system, as Andy mentioned. In between here, oops, let's see. If you see in between the C48 Constellation racks, we're using APC in-row heat exchangers, which carry about 90 to 95% of the heat load of the entire system. So that's why it's actually enclosed from the top, because you want to get all that hot air into the heat exchanger so they can be very efficient. This is a very long project when you look back from the beginning, from when we actually wrote a proposal, sitting down with Andy and folks to actually put together the design of the system. So we're looking at over about 2.5 years of initial planning and development, if you can believe it. It's funded by the National Science Foundation as part of a new program that they... Sure. Check 1, 2. Better? Sorry about that. Everything I said was really clever so far. So anyway, the program is funded by the National Science Foundation. This is what's referred to now in the field as the Track 2 Awards, and it's really intended to try to reinvigorate high-performance computing in the U.S., kind of in response to what Japan had been doing with the Earth simulator and the amount of money that Japan was investing. The U.S. realizes they are falling behind a little bit, and so this is sort of the first attempt to try to reinvigorate HPC in the U.S. So there's the Track 1 solicitations, which there are at least going to be 4 of them. There was also the Track 1 award, which you probably heard about, which was a slightly bigger investment, $200 million. So the first Track 1 award, what you could spend on the system was $30 million for the system acquisition. Obviously, Sun was our partner in this proposal, and it is really all the time, all InfiniBand all the time. So in the end, we ended up getting 2 Magnum switches. So that gives about 4,100 endpoint hosts and 1,350 of the Mellanox i3 switches. And at the time when this solicitation came out, we were competing against just about every open science HPC center, and we had a number of partners involved with this in addition to Sun, a number of academic partners, because you don't build something like this by yourself. And so this just lists some of our partners, ISIS, who are application experts, and we have partners at Cornell Theory Center and the Arizona State High Performance Computing Center. So $30 million for the system. We are obligated to operate the system for 4 years, and the M&O budget for that is about $29 million. So in terms of, I said this is about 2.5 years. You go all the way back to February of 2006 when the original proposal was actually submitted. The award was announced in September of 2006. We began, we did a lot of initial testing, but we began main construction of the system in the second quarter through the fourth quarter of 2007. We had users on in December of 2007 with people calling me on Christmas Day, wondering why they couldn't run jobs. And then we started formal acceptance testing on January, and then we went into full production in February of this year. All right, so the actual date we went into live on February 4th. So what I'm presenting here is sort of experiences through the deployment and about 4 months of initial operation. I think Andy showed this slide. I just like to show it because it kind of gives you a feel for all the people who participated and collaborated. This is actually, we have two plots like this. One is for all the people who helped build the system, and then one for all the users who are currently using the system. And to be honest, it looks very similar. And the point is just to show that this really is an international effort. We have folks all over the U.S. helping out, all over Europe and Asia as well. And the other thing I like to point out is that this is really an example of leveraging open source technology for Ranger. We're running Linux, we're using open fabrics, we're using Lustre, we're using publicly available MPI stacks, and it's actually crucial for us to be able to take all of the best available software stacks and have the source code so that we can integrate it all into a local software stack and have it working with our kernel and patch it to get the hardware counters. So I think it's a good example of sort of taking the best in breed that's available to the HPC community. So going through the hardware summary, it is, as originally scoped, 504 teraflops, which we get out of almost 4,000 of these quad socket blades. We do have a fair bit of memory on the system. We always, at least at TACC, we try to adhere to keeping 2 gigabytes of memory per core. So it gives us pretty fat nodes since they're quad socket nodes. That's 32 gigabytes of memory per node. We do measure a little over 20 gigabytes per second of stream memory bandwidth. The disk subsystem is 1.7 petabytes raw that we get out of 72 thumpers. Now, it turns out we didn't build just one big file system because we've done this a time or two, and we recognize that the parallel file systems is going to be one of your, one of the things which is likely to go up and down just because it's pretty complicated software stack. So what we did is we actually broke up our 72 thumpers into 3 unique file systems. We actually run home on Lustre, and we also have 2 other scratch file systems that we use that are high-performance file systems that we make available for our users to run jobs. In terms of the largest file system, we have about 1 petabytes raw capacity, and I'll show you some performance numbers, but just to give you a feel, we get roughly about 40 gigabytes per second to this big file system. Interconnect, Andy talked about the Magnum switches. As I said, we have 2 of them now, so because we have 2 switches the way that they're integrated, it means we actually have a 7-stage cross fabric. We're using the ConnectX HCAs, and I'll show you some specific latencies in a little bit. Now, Ranger is 82 compute racks. It's almost 4,000 compute nodes, so you need a lot of management infrastructure as well to drive this system. So we actually have essentially another small cluster to manage the big cluster. We have 25 management servers, which are predominantly Sun 4600s. So we have 4 login nodes that we actually, that's how our users come into the system and interact with it, is via 4 login nodes. We have a provisioning node. We run SGE on the system, so we have primary and backup servers for SGE. We have Sun N1SM management servers. We have a couple of servers dedicated to just do the subnet management for InfiniBand, and then, of course, a number of servers to drive Lustre. So we're using thumpers. I'll talk about that. But in terms of our metadata servers, we have 4600s actually hooked up to some fiber channel storage tech disk, exactly for the reasons that Andy talked about, is that you need more IOPS for your metadata servers. And so that's what we're doing there. We also have some special nodes that we use to access our archive facility. So, Ranger is generating huge amounts of data, and I'll show some examples at the end, but we need to be able to get that data off of the system back into some sort of permanent archive facility. So we have a SAM-QFS implementation, and what we have done is we've identified a set of nodes which sit upstream of the SAM-Q disk, and then a set of nodes which sit on our Ranger system, and there's 10 gig E connectivity between those 2 sets of data movers. And that way we can allow users to hop on these data mover nodes and move, they can use grid FTP or the like to move data between our Ranger file system and our archive file system in a quick manner. So I mentioned that it's pretty much InfiniBand all the time. We don't have Ethernet to any of our compute nodes, but we do, as part of our work with the National Science Foundation, Ranger is connected via 10 gig E to 2 external 10 gig E networks, both TeraGrid, which has a private 10 gig E network actually across the country to TeraGrid sites across the US, and we also have 10 gig E connectivity to MLR. All right. So talking about the InfiniBand cabling, one of the big advantages in going with the Magnum-based solution was the use of these 12X cables, right? And so, just to kind of highlight what they do. They're really just aggregating 3 4x connectors onto one single cable. So you can imagine when you actually need to hook up to a 4x connector, you need some sort of special cable here, which is what we call a splitter cable. But it really kind of drives the point home of how you're aggregating these cables. And the long story short here is that Ranger's a big system, and there's still a lot of cables. Okay, there's over 1,300 InfiniBand cables, but it turns out that's actually fewer than the number of cables we have on our other cluster, which is a 1,400 node cluster. So we want to say that it's still a challenge, but it's at least lets you attempt to build something like this because you've aggregated the cable counts. So we've got 1,300 of these 12x cables. We have 78 of what we're calling these splitter cables. That actually hooks up to our I/O subsystem and all of our management infrastructure. And we have a number of different cable links installed in the system. So our max cable run is actually 16 meters, and that's for one of these splitter cables. And then in terms of the pure 12x connectors, our max run is 15 meters, and our shortest run is 7 meters. And then I think Andy showed this slide. This just kind of outlines the fabric connectivity. I only like to show this. The main thing to point out is people usually ask me, well, how do you connect the cables between the two magnums, right? And you don't connect the cables between the two magnums because embedded into the C48, if you could see the back, essentially there's something called a NIM, a Network Express Module, which is really a fancy name for a leaf switch, which has these 12x connectors. And so what we do is we connect, coming out of these leaf switches from the back of the C48s, half of the cables go to one magnum and half go to the other magnum. So that's how you have a full view of the entire topology. So there actually isn't any, you'll notice there's no cables hooked between the two magnums directly. They have a view because of the leaf switches. And then you might be interested in sort of the overall power and cooling of the system. As designed, we have about 3 megawatts of power delivered into our new machine room. And the design was to provide about 2.4 megawatts for the system. So I said we have 82 compute racks. If you count up all the racks, which include our management infrastructure and all of our I/O nodes, we have about 90 racks. They're laid out in a 6-row configuration. I talked about we have these in-row coolers, so that kind of expands the floor plan a little bit, but it turns out that they turn out to be very efficient in terms of their cooling capacity. So we have 100 of those. And if you look at the whole footprint of the system, you're looking at about 4,000 square feet. Right? And a lot of that is actually coming from these in-row cooling units. The density of the C48s is actually quite high, but you get expanded a little bit because you've got to dissipate so much heat. In terms of cooling, we're looking at about 0.6 megawatts for the cooling infrastructure. We drive that with 3 400-ton chillers, and you saw a picture that we have enclosed hot aisles. We do actually have some traditional crack units in our machine room. We have about 7 crack units which provide 280 tons of cooling. Turns out that we don't actually even leave these on all the time. We leave about 3 of them on, and their main goal right now is just to get humidity out of the machine room. They're really not doing a whole lot of cooling. So these are peak numbers. If you're interested in kind of what it actually does when the system is running with sort of a normal user load, what we see is more like a draw of about 2 megawatts for the compute infrastructure, when the system is running under normal operating load. And just some observations here, the multi-core is really making space less of an issue, but unfortunately it's making power a disastrous issue that we all have to face. We had to have a design which would cool greater than 25 kilowatts per rack, and so that's why we're using these in-row cooling units. And in this particular installation, one of the challenges was power distribution because the racks as they stand now are still being driven by 240 power, and so we had to deliver more than 1,200 circuits to the 82 compute racks that we have in our machine room. And just to show some pictures of the deployment, I mentioned we have 3 400-ton chillers, just to get a sense of the size. There's your basic 18-wheeler dropping this thing off. It's all built to have N+1 redundancy, so that's why there's 3 of them. It only takes 2 to cool the system at one time, with the only caveat being that they tell us there's a few days in August when it gets really hot in Texas that there's a good chance that all 3 will be on. So we might have to limit the queues a little bit on those days. And this is what we're looking at. We have a dedicated, we have our own closed chill line. So our campus, a lot of the universities have their own chilled water supply, and that they deliver to all the buildings. But in this case for Ranger, what we did is we built a standalone closed loop chilled water supply. And what we're looking up here on the top right is some of the infrastructure required for that. And this is some of the electrical work that we have to provide the 3 megawatts coming into the building. So what it looked like when C-48s were showing up. We uncrated them outside and hoped that it didn't rain. And lucky for us, it didn't. And oops, sorry. Anyway, yeah, that's what it looked like when they were unloading. This is what the 2 Magnums looked like when they showed up before they got cabled, all nice and pretty. You know, as you notice, there's a nice cable management infrastructure on the sides of these things. I think your thing is trying to tell me to go fast. It keeps moving on me. It's hinting at things. Anyway, so those are the 2 Magnums pre-cabling. This is what they start to look like after the cabling process. You'll notice that kind of what we're doing here is testing cables, so it sort of looks like the thing is almost vomiting or something from the front, and here we go. This is, am I jumpy? Am I jumpy? Let me not touch anything. Okay, so that's an example of what the switch looks like as it's cabling. I got a couple more pictures later on. I did want to go over a little bit some information on the HPC software. So one of the things that we did in collaboration with Sun is, we have a fair bit of experience doing HPC Linux clusters, and so we sort of architected the software stack in this case, and this is kind of what we ended up going with. So we're using CentOS, which is just a free version of Red Hat based on the RHEL 4 sources. So we're at RHEL 4, we're not yet at RHEL 5. We're using a very specific kernel, which it turns out is somewhat interesting because it's the intersection of many things. Thank you. It's the 2618.8 is the latest that was supported from Lustre at the time. And so that was one key ingredient. We're running Lustre, so clearly the kernel has to have support. The other key thing that we're always looking for with InfiniBand, if you've been doing InfiniBand for a while and you've been doing HPC applications, you know that there have been some nasties in the past where applications can't fork off, and because of the memory pinning that is done in the OFED stack. And so one of the things that we were trying to use was a very new kernel which have a different memory subsystem so that we could actually provide fork support to all of the users. And so 2618 actually accommodates that. So it was a kind of a sweet spot. So that's why we're using a kernel.org kernel as opposed to a RHEL 4 kernel. We do make specific modifications, obviously, to the kernel for Lustre. We also make modifications to get access to hardware counters. So the new Barcelona processors have 4 counters on the chip that you can access simultaneously to get hardware counter information. So we do patch the kernel to get access to that. We're running the OFED stack. So OFED 1.3 wasn't out when we were doing the deployment. We were using a sort of pre-release version of OFED 1.3. It's 1.25.4. We've upgraded Lustre a few times during the deployment, so I'm showing here what we're running at now, which is was the latest in the 1.6 tree. We use ROCs for our provisioning, but really the way that we use it is for provisioning just once, and then we kind of use our own software to take over the management of installing new software. And we are using SGE. It was, I guess the name sort of changed at some point. It was N1GE for a little bit, and I think now it's back to SGE. So we're using SGE as our batch scheduler on the system, and we use N1SM to monitor some of the service processor logs across the entire compute infrastructure. And then in terms of the subnet manager, we actually have 2. I'm listing IBSRM here, which is the Sun version. It turns out we actually also use the version from OpenFabrics, which is called OpenSM. But this is the baseline sort of driver stack, if you will, for the system. And then in terms of the user stack, what the user actually sees in terms of being able to compile and run jobs on the system, we have a number of different compiler families. We have the Sun Studio compiler, PGI compiler, and Intel, believe it or not. I know it seems strange to have Intel on an Opteron-based system, but we still have examples where the Intel compiler can actually provide faster turnaround times than any of the others. So that's why we continue to make it available. Their compiler group is actually quite good. In terms of MPI stacks, when we were going through deployment, it wasn't really clear what would end up being the best MPI performer on the system. So you'll notice we have 3 different stacks. We have MVAPITCH and MVAPITCH2, which both come out of Ohio State, but one of them is a full MPI2 implementation, and the other is an MPI1 implementation with some extended semantics for MPIO. We also have OpenMPI, which is, if you're familiar, is a fresh crack at an MPI implementation which is not built directly from the Argonne version. So what we have, you can kind of guess our software matrix for things that we have to build and support is quite large, because for every compiler stack we have to have an MPI stack, and then any third-party libraries that we build using MPI, we have to have a separate tree for that as well. So the way that we control all of that on the system is via an oldie but a goodie that I think came out of Cray a long time ago called modules, which is just a nice way to control the user environment. So essentially what you can do is you log into the system, choose whether you want MVAPITCH or MVAPITCH2 or OpenMPI, and then under the covers it kind of sets up that environment for you automatically. In terms of debugging, well, clearly it's Linux, so GDB is always out there. One of the things that we do allow on our system is when you're running a job, all of our usage of the nodes is exclusive, so you can be guaranteed that if you have a job on a compute node, nobody else does. So because of that, one of the things that we do is we allow users to be able to access that compute node. So you can actually log in the compute node, you can run GDB, you can attach it to specific processors, you can run top, all those kinds of things because you own the node. So that kind of base level debugging is always available. We also have a graphical debugger on the system called DDT, which we're working on now in terms of sort of the scalability, but we've been able to do graphical debugging in sort of the 2,000 to 4,000 MPI processor range so far. So just to give you a feel for some of the challenges, any big installation is going to face some challenges. So some of the stuff that we ran into up front was some manufacturing issues with the IB cables. Obviously, a big thing in the news was the quad-core processor delays, and lots of BIOSes. It's new hardware. It's coming out, so you can expect lots of firmware updates. So that's kind of the usual stuff. One of the things which you don't expect is sort of external forces jumping in beyond their control. So I don't know if y'all can actually read this, but I call this the Darwin effect. And the title here, this is from the Austin News, and it says, "Man catches fire trying to steal copper." And what actually happened was a guy was trying to steal a grounding rod from one of the main substations. And so he essentially caused a minor brownout in the city. And although our compute node stayed up, it took our magnums down. So this was actually one of our downtimes was this. And then, so that's kind of hardware challenges. In terms of software challenges, you're really expecting to have scalability problems with just about everything, and that's kind of what we faced. We also had some issues up front with, at the time, we were using the brand new ConnectX cards, and so that meant having to use a later version of OFED than was currently supported with Lustre, so we got to work with the Lustre folks to sort that out. Dealing with the RAID 5 implementation on the thumper boxes and quota issues were some of the challenges we faced. Something that you kind of thought was probably going to come up is this is probably the biggest InfiniBand topology that exists out there right now. So some poor piece of software actually has to map that InfiniBand subnet. And the first time we did this, we were sort of shocked to see just how long it actually took to map all of the routes. And it took over 30 minutes with IBSRM the first time we had both magnums and all of our compute nodes available. But that now I'm happy to say has been reduced using other subnet managers down to on the order of about 2.5 minutes. Sun Grid Engine, scalability stuff, performance thing. We had a lot of interaction with our colleagues in Germany who helped us out to kind of get Sun Grid Engine running on all 4,000 nodes. And we also had some issues with collective tuning and large job startup. So let me skip over this one since I'm running slow and show you job startup. This is kind of an interesting one. We've had experience in the past. Our other cluster can accommodate job sizes on the order of about 4,000 processes. Ranger with 62,000 cores, what you want to do is see how big you can launch a job. And one of the things that we ran into up front is, if you see this plot here, what I'm showing is what it takes for the most basic of MPI applications, how long it takes to run that. Okay, and you'll notice here that at 10,000 tasks, and this is a log plot, you're into the many, many minutes of of job startup time. And I think the first time we did a 16,000 core case, it took about 15 minutes to actually run the job. Right? So clearly that's unacceptable, and that's a job startup issue. So we had some collaboration with the folks at Ohio State who were responsible for one of the InfiniBand MPI stacks. And what they did is they wrote a new job launching mechanism. You know, it's kind of what you would expect because most people are used to not dealing with multi-core, and so they were launching one task for every single MPI. You know, we've got 16 tasks per node, and there's really no reason to do that. You only need to do one. You need to fork one thing per node. So that's one of the things that they did. And what you see here is the fruit of those efforts where, you know, you can launch here. I think what I've gone